Buenos días a todos. Me llamo Dmitry Aldakov. Voy a hablar de síntesis de nanopartículas de semiconductores. Es un curso por la Escuela NanoAndes, pero hablo español no más bien, entonces voy a hablar en inglés. So the talk of today, the class is called the Synthesis of Colloidal Nanocrystals, and I work in the laboratory SIM, which is synthesis of molecular nanomaterials for energy and health, and the lab is a joint unit between CNRS, CA, and the University of Grenoble-Alpes. You have heard about, you have had already several courses on synthesis of nanocrystals, on some generalities. I will just mention it very briefly because you've had it by Sarah, by other people. So I will mention something about quantum confinement, about crystallization and the growth mechanisms. And then I will give you some examples, for example, the synthesis of cadmium selenide, and I will take this advantage to explain what is hot injection. I will talk about how can we control the nucleation and growth of nanocrystals. I will talk about core shell nanocrystals using as an example cadmium selenide zinc sulfide. I will talk about the synthesis of indium phosphide and its particularities, magic size clusters, a gradient shell. Then I will switch to ternary nanocrystals such as copper indium sulfide ones, non-toxic ones. I will explain a little bit about ligands and aqueous synthesis, and I will finish talking about perovskite nanocrystals. So, the quantum confinement effect is a physical phenomenon which is derived from a particle in a box, meaning that when we reduce the size of the object, we increase the kinetic energy of electrons, and the electron and hole start to interact, and they don't have enough place to find place in the material, in the nanoparticle, and the energies start to quantize. So the smaller we get the nanocrystal, the more energy levels are quantized, and the higher we get the band gap. The direct consequence of this is that by playing with the size of these nanocrystals, we can change their optical properties, such as absorption and the photoluminescence. So we control their size just by changing the synthesis time. We control the band gap, and we can shift the emission, we can fine-tune it. That's why we can do it for several semiconductors, common ones like zinc selenide, cadmium selenide, lead sulfide, and so on. And as you see here, the range of emission, it's a range. So by tuning the size, we can really emit at the given wavelength if we find a good size of them. So those are most common semiconductors which we can make in colloidal form. A couple of words about colloidal stability. Colloidal stability is maintaining the stability of nanoparticles in different solutions. It could be in organic solvents. In this case, we talk about steric repulsion. We have long aliphatic ligands usually. And if we talk about aqueous synthesis, we talk about electrostatic repulsion because those ligands or the surface of nanoparticles is charged. That's why we have the interaction of charged species. And this stability is defined by what we call DLVO theory, Dyragin, Landau, Verwey, Overbeck, who have developed it in the 50s. And it's basically the interplay between two main forces, electrostatic repulsion or steric repulsion, which increases as we approach nanoparticles, and against the van der Waals attraction, which increases when we approach nanoparticles. So there is some potential barrier, intermediate part, which allows the nanoparticles to stay stable in solution. If they don't have this steric repulsion or electrostatic repulsion, they will just coalesce and precipitate because they want to minimize their surface energy. And then this is this principle which helps maintaining these colloids stable in solution. In chemical synthesis of colloidal nanocrystals, or quantum dots as we can call them, one of the most common is called a hot injection method. In this case, we use if we take as an example cadmium selenide, we put cadmium precursor in the solution, we make the injection of an ion, we heat it and we inject it very rapidly. We create supersaturation of the monomers, and they start to react with each other, cations and anions, and they start to create clusters. We have nucleation threshold, have nucleation, and then we have growth and gradual decrease of the concentration of the monomer and increase of the size of the nanocrystals. So this is the principle of all of main growth mechanisms of colloidal nanocrystals. The size control of those nanocrystals is defined by what we call Lamer theory, which you have probably heard already about. And the key in this strategy and this mechanism is the separation of nucleation and growth. Because if you have a continuous nucleation, you will have some particles which will grow faster, others slower, and you have very wide size dispersion. While by separating them, by creating supersaturation, you can control it. So first you inject your monomer, you create a lot of nuclei, and then they grow, and they stabilize at the time, at some time. In the beginning, the driving force of reaction of the monomers is the gain in the chemical potential. The monomers, precursors, they want to react with each other, they create chemical bonds, and this is, you free the energy like this. This is an energetically favorable process. So I have first question for you. So what do you think if we in solution we have this crystallization, nucleation and growth, and if we increase the supersaturation, if we increase the concentration or injection rate of the nanoparticles, or of the monomers, will it result in larger final particle size? So we have more monomer, we inject it faster. Logically, it should result in larger nanocrystals, right? I'll let you think just a few seconds. In fact, it is wrong, because we increase supersaturation, we create more nuclei more rapidly, and then each nucleus start to grow, and it consumes more and more monomer, and like this we get more nanoparticles which are smaller. The overall concentration of nanocrystals will be larger, but their size will be smaller. And if we make it slower, we use lower concentration, it's vice versa. So it's a very interesting phenomenon which allows us to control the size of these nanoparticles. After a while, after some time, after the growth of nanocrystals, we can get a phenomenon, another one, which is called Ostwald ripening. It means that you have a mixture in your solution of small particles, large particles, and then at some point small particles start to dissolve and release new amounts of monomer, which reacts and grows on the surface of large nanoparticles. So you have a gradual disappearance of smaller nanoparticles, and you have growth of larger and larger particles. This is an example, for example, for palladium nanoparticles in formaldehyde, and in some time, in several hours, you get only large particles which have consumed all small ones. It means that you increase the size of them, but you decrease the amount of them. So this is an interesting phenomenon. If we wait long enough, we can have it in most of the nanocrystal growth mechanisms. We can also control the nanoparticle size by some other methods, for example, easily by temperature. We increase the temperature, we increase the supersaturation, we create more nuclei, and that's why at the end we have smaller size. If we increase the concentration of the stabilizers, like ligands and so on, we slow down this nucleation process, and that's why at the end we will have larger size. In some particular cases, in addition to Lamer model, you can have Okana model, where you have nucleation, growth, and then aggregation of nanocrystals. Not Ostwald ripening, consumption of small ones to profit the large ones, but coalescence of similar sized nanocrystals. And you can have Sugimoto model, a Japanese scientist who have provided an example of multiple nucleations. So we have several steps of nucleations and then growth via ripening, via Ostwald ripening. The most common example, as I mentioned, for nanocrystals is cadmium selenide. The first publication of the colloidal cadmium selenide was in 1993. This is a very popular publication in JACS. It's a group of Munji Bawendi who provided UV spectra of the shifting maximum of absorption and photoluminescence, very small Stokes shift, a pretty nice quantum yield, and there was very nice size dispersion. And it turns out that this paper is extremely well cited. So it's so far by today it has been cited for 7,000 times. Because it was a really seminal work which inspired a lot of scientists all over the world that it is possible to make this stable colloidal and luminescent nanoparticles. Today's understanding of the growth is we use the solvents. Usually it should be, of course, inert solvents which will not react with anything, and high boiling point solvents, because usually the synthesis takes place at above 150 degrees, 200, 300. That's why very often they have long aliphatic chains. So one of the classic ones is octadecene with one saturation. You have topo, trioctyl phosphine oxide, and also you have ligands to stabilize nanoparticles and precursors in solution. You have this HDA, hexadecylamine. You have oleamine. So usually ligands have functional group which can bind to a precursor and so on. And some of them can be both ligands and solvents. This is the case, for example, of dodecaine thiol, because it's liquid, it's highly boiling point, and it can also stabilize precursors, and oleamine. While preparing the synthesis, care should be taken for the purity of the precursors, because in, for example, topo you can get 90%, 95, 99. Oleamine is very often its technical quality, and it can introduce some impurities in your synthesis, and it will be much less controlled. How can we control the nucleation and growth using chemicals? Well, initially people used just coordinating solvents where solvent was a ligand, like topor or HDA. It's practical because you have just one precursor, but the problem is that you cannot control the relative amount, the concentration of ligand. That's why more recently we use non-coordinating solvents like octadecene and the very precisely defined quantity of ligands, so in two separate solutions. We can tune the nucleation and growth by stabilizing ligands. For example, the bond strength, functional group strength. If you use phosphonic acid instead of carboxylic acid, they more strongly bound to nanocrystals, to precursors. That's why they slow down the nucleation and they affect the growth. You can play with the steric hindrance. It means that the length of the carbonaceous chain, the bulkiness of it, and the concentration, of course, of the ligands. All this can increase can lower the reactivity of the ligands, lower number of nuclei formed as a consequence, and at the end you will have bigger nanocrystals after growth. And all this is just playing with ligands. So if we come back to the classical synthesis of cadmium selenide, hot injection ones, now the most efficient one uses a cadmium precursor, cadmium oxide, some phosphonic acids like this, DDPA, some solvents like topo or hexadecylamine, which serve also as a ligand, and we inject selenium in trioctyl phosphine. They react at high temperature, and we use coordinating solvent, and this solvent is a surface ligand. So for cadmium selenide we can control their size in a pretty large range from 2 to 7 nanometers just by playing with the ligands, with the ratio, and with the temperatures. However, after the synthesis, the quantum yield, it means that the efficiency of the photoemission of the nanocrystals is not very high. It's less than 10% in case of cadmium selenide. It is number of photons, emitted photons per absorbed photons, and it's considered as to be limited by surface defects, trap states on the surface, uncoordinated atoms, and so on. There is a very nice way to improve it, is to passivate the surface of those nanocrystals with other semiconductors with larger band gap. First example of this was published in 1996 by a group of Guillaume, and they have demonstrated that when they add zinc sulfide shell on the cadmium selenide, the absorption of the nanocrystals almost doesn't change. However, the photoemission, it increases about 6 times, and they still get nicely monodisperse nanocrystals with nice properties. And this paper also has been widely cited more than 2,000 times, and it has also launched a new field in the nanocrystal synthesis. So as I mentioned, this shell, it improves the photostability and it enhances the photoluminescence quantum yield. What should we think when we choose the shell material? First is lattice mismatch. Not all materials are compatible with each other from the crystallographic point of view. As you know, in the crystal you have lattice parameter, the characteristic crystalline size between the atoms, and if it's not matched between core and shell material, you can have all types of distortions, deformations, and so on. That's why when you choose the shell for your core, you need to think about matching these lattice parameters. And for example, for cadmium selenide, it has a wurtzite structure, and one of the parameters is 4.3. And it's better to take something, the shell material, which is close to this lattice parameter. For example, zinc sulfide is pretty good. However, if you want to take, let's say, I don't know, indium phosphide, and cover it with what? With let's say cadmium telluride, it will not be very compatible. Another parameter to keep in mind is band alignment. In physics, there are 2 types of major band alignments: type 1 and type 2. Type 1 is when shell material has a higher LUMO conduction band and lower HOMO valence band, and it means that you have confinement of the exciton in the core of these nanocrystals. In this case, the classical example is cadmium selenide, zinc sulfide, and you have confinement and protection of this exciton within cadmium selenide. While if you use type 2 nanocrystals, you have ladder-like heterojunction alignment, energy alignment, and you have charge separation and the interface between core and the shell, and you confine your hole inside of, in this case, cadmium telluride, and your electron will be in the hole. This alignment is very interesting if you use electronic applications, if you want to separate your electron and the hole, for solar cells, for example, for photodetectors and so on. While this is more interesting for photoluminescence applications, because you want to have your exciton and which will be luminescent afterwards. So here you have some types of type 1, type 2 systems. You can get type 2 with the hole in the core, or hole in the shell. You can get reverse type 1. You can have core shell with multiple shells and so on. You have a wide variety. Just you need to pay attention to the position of the energetic levels of the materials for your core and the shell. How can we synthesize the core shell system? First is the simplest one is one-pot injection. You make first your nanocrystal synthesis by hot injection by something else. Then you can purify, or sometimes not. You can use just the solution as is. And then you inject the shell precursors. Usually we use syringe pump to control the amount of precursors which we put into solution. And you have your in situ growth of the shell. Alternative way is to make SILAR, successive ion adsorption and reaction, and its name tells for itself. Actually, you take your core nanocrystals, you inject first cadmium precursor, just the cadmium, which adsorbs on the surface of these nanocrystals. You have to calculate very precisely amount of your concentration of your cadmium as a function of concentration and surface area of your nanocrystals. Then you inject sulfur, also very precise amount of sulfur precursor, and you get one monolayer of your shell. Then by repeating this procedure several times, cation anion, you can precisely atomically control your shell to the given thickness. This is a very powerful method and also very widely used, even though it requires a little more preparation than one-pot injection. So far it's been very nice. I have shown you a lot of examples using cadmium selenide. However, it has one very important drawback. It's toxic. It contains cadmium, and as you know, cadmium is a heavy metal, and we don't want it in our environment. In addition, it is, as a consequence, it is also very strictly controlled by Europe, by world agencies and so on, especially if you want to use it in solar cells, in biolabeling, of course, in light-emitting diodes and so on. So something has to be done, even though it's a great material, something needs to be done to replace this cadmium. If we look at the table of possible alternatives, we know that there is one material, indium phosphide, which looks pretty good for this application. Its emission has emission in the visible and so on. And indeed, we can make nanocrystals of this material. It has bulk band gap of 135, which is in the visible, which is very nice for different kinds of applications. It has exciton Bohr radius of about 10 nanometers. For the same size distribution, it has width at half maximum, slightly larger than cadmium selenide, but it's not significant. It doesn't have, you see, it doesn't have any toxic ions such as lead or cadmium, and indium by itself is not toxic. It is already used in vivo. If we look at some synthesis of this indium phosphide, we see that the conditions of this are much harsher to synthesize compared to cadmium selenide. The reason is that indium phosphide is more covalent. The bonds inside is more covalent, and you need more persuasion to convince it to react. So, for example, either you can use a very reactive compound precursor, which we call PTMS, trimethyl phosphide. It's very reactive, but it has a downside. It's too reactive, so it's pyrophoric. It can explode, and it's toxic. But well, it makes this very nice complex, and it brings this indium close to phosphorus, and it makes very nice intermediates, and we can get indium phosphide at the end. Another way is to heat it to high temperatures, to 270, 300 degrees, but you need to heat a lot. You need to heat for 3 and up to 7 days to get something large enough nanocrystals. You can get size-dependent optical properties, but for this you cannot just rely on the synthesis time. You need to make size-selective precipitation, and still your sigma, your size dispersion, will be maximum 20%. So it's really tricky material which needs to be treated with care. And so the synthesis of it in the lab looks like this. You mix indium salt, in this case indium acetate. You take myristic acid. As you have guessed, this is a ligand. It has it's a long chain, and it has functional group in non-coordinating solvent, and you inject this very reactive precursor PTMS in octadecene, and you have growth, and you can get nice absorption, nice size dispersion. Photoluminescence is not very good. It's really wide and not intense at all. And you see, nice. The size distribution is only 15%. The size range you can get only 2.5 to 3.5 nanometers, and photoluminescence quantum yield it's pretty low. So some alternative synthesis methods are needed. But why is it so different? If we compare it to cadmium selenide, we see that in cadmium selenide you have a very nice clear separation of nucleation and growth, strictly following Lamère diagram. We have what we call size focusing, so above a certain size of the nanocrystals you get narrowing of the size dispersion of these nanocrystals, which is not the case at all for indium phosphide. And finally, you have size tuning at full yield. It means that it's also an interesting phenomenon. As I said, you can control the properties of nanocrystals just by controlling their size. The size you can control by stopping the reaction earlier or later. But if you stop it earlier, you waste a lot of material, a lot of monomers which have not reacted yet. In this case, you can play with the reactivity, with the supersaturation, with the concentration of ligands, with the rate of injection, with the ligands, and so on, and you can get this size tuning even at full yield. And this is much harder to achieve with the indium phosphide once again. It seems that it doesn't follow conventional growth mechanisms. And if we take a closer look why it is happening, so we see first of all that PTMS is so reactive that within 1 minute, less than 1 minute, it reacts already completely. It binds to myristic acid and it's not active anymore. And we see if we take absorption spectra at different times after the synthesis, and we see that at the early times you have this band, this peak at about 360, 370 nanometers, and it doesn't move. It just stays there, it just decreases. And as it decreases, you have increase of excitonic peak of indium phosphide. So something else is happening at early stages, and something very well defined. It turns out, after a lot of work of different persons, different groups, that the synthesis doesn't follow classical Lamar theory, and it proceeds via what we call magic-sized nanocluster. Nanocluster is something, it's an intermediate which has about 100 of atoms. It has a very precise size, and it has some relative stability. So first you have reaction of these ions, indium and phosphide, at the beginning, which make these nanoclusters, which stay for a while, and then they dissolve little by little. They release new amounts of monomer, which react, and you get this indium phosphide. So you have this intermediate stable state. This is a ripening type growth, and these magic size clusters, it's a very interesting thing. You can isolate them, taking some precautions, but they are relatively stable. They can be used as precursors for different synthesis of other nanocrystals. You can isolate it and use it for different synthesis, and they can even be used for applications directly, for light emission, for white LEDs, and so on. It's a special field in the research, and it is very interesting. That is why it is so different. The kinetics of the growth of this indium phosphide quantum dots is so different, because it has this stationary, pseudo-stable state. Meanwhile, people in our group also have developed other synthesis of this indium phosphides, getting, for example, here we can mix all together zinc selenide, the zinc sulfide and indium phosphide in one pot synthesis. It's not hot injection, it's one pot heating up synthesis. We get size tuning, we get a nice quantum yield. We can replace this pyrophoric and toxic PTMS, which is also very expensive, by zinc phosphide. In this case, we take this zinc phosphide, we treat it with sulfuric acid, we generate in situ phosphine gas, which we bubble again through the indium precursor, and in situ we get this indium phosphide nanocrystals with a very nice quantum yield. We can get some color tuning and so on. And finally, what we can do is we can get gradient shell. It means that it's not just one shell step another shell. It's gradient shift in automatic gear cars. You use two shells which you gradually alloy. So you use first the zinc selenide because it alleviates lattice strain, because indium phosphide and zinc selenide, the lattice strain mismatch is pretty large. So first you use zinc selenide, and then gradually you move to zinc sulfide, and this one protects against degradation and non-radiative relaxation. And like this we can also get a very high quantum yield. Another example of non-toxic, less toxic nanocrystals is copper indium sulfide. This is what we call ternary, because it has three different atoms, ternary nanocrystals. And we can imagine it deriving from cadmium selenide. If we take divalent cadmium and we replace it by a monovalent and trivalent cations, we get this copper, indium selenide or sulfide nanocrystals. As you will see, it's much easier to synthesize them compared to indium phosphide. They are non-toxic, they are stable, very stable, they are highly absorbing. They have very nice electronic properties. It's very cheap, and it can be scalably synthesized. And the band gaps are indivisible, as you can see, also very interesting for solar cells or for emitters. Its synthesis, usually it's the most classical is heating up synthesis. We mix everything together, we heat, and we create supersaturation by using temperature as an energy source. We can control the ratio between copper and indium. We can get alloys in a pretty wide range. If we use mixed solvent, DDT and octadecene, we get lower size distribution even though the temperature of the synthesis is lower. If we use just the DDT, we get nice monodispersed nanocrystals and high reaction yield. So usually the synthesis takes place at 100 degrees at the beginning. We get transparent solution, then we heat it more at 230 for 1 hour. But you would say, what is happening there? Because you haven't seen so far this strange synthesis. It's not hot injection, it's not magic cluster. What is it? We try, and a lot of people use the synthesis without understanding what is happening. So we try to dig more into the mechanism of this synthesis. We use the synchrotron radiation here in Grenoble, the synchrotron, to study in situ X-ray diffraction of the initial moments of the synthesis. And we see that we couple it also with the NMR studies of also during the growth of these nanocrystals to study the ligand shell, because we can get the diffusion coefficients and so on. And it turns out that at 100 degrees our compounds start to make these clusters of well-defined size. They are already half crystalline, and then if we heat it to 30 degrees, our sulfur loses its organic tail and it becomes a precursor of the sulfide in the nanocrystals. So this is quite unique synthesis, because in this case DDT, dodecane thiol, serves 3 roles. One is it's a solvent, second it's a ligand, and the third is a sulfur precursor, because at 230 you start to decompose partially this compound and it starts to react, making this cores. So this is a pretty unusual and interesting and efficient synthesis. I should say a couple of words about aqueous synthesis of nanocrystals. Usually the logic of making the reasoning why we are interested in aqueous synthesis of nanocrystals is pretty simple. Well, first we use water is non-toxic. We want to get rid of organic solvents, which are in addition more expensive. Organic solvents always you pay some extra. And finally, the very nice advantage is that you synthesize nanocrystals directly in water. You don't need to transfer them, because for a lot of applications, for bio applications, for photocatalysis, very often you use it in water, and if you synthesize it at the beginning in organics, you have to make this phase transfer, ligand exchange, and you lose some of your nanocrystals, you lose some of your emission and so on. While in water, you have them already in water. The principle is simple. You take water-soluble metal salts, halides, nitrates, acetates, and you use some surface ligands in water. The potential ligands and precursors you can see here. Usually it's bifunctional or trifunctional molecules. They have thiol function, which binds to the core of nanocrystals, and let's say carboxylic acids or amines to make this to make them soluble in water when you ionize them. Typical synthesis for colloidal semiconductor nanocrystals is you have hydrothermal synthesis. You just mix everything together, you close it in an autoclave, you heat it, you get a low-cost, really simple synthesis, which gives you a good reproducibility. You can also get it by microwave. In this case, the advantage is that you work at normal pressure, you don't have a risk of burst. Usually you get smaller nanoparticle sizes. The reaction is faster because you excite just the bonds you want, not everything, and you get good purity of the product. Also, you can heat it just in the flask, but usually it takes longer time and you get less good size dispersion. So this is an important field also in the nanocrystal synthesis. One word about purification of nanocrystals, because it makes part of to me it's a part of the synthesis. If you synthesize good nanocrystals but you cannot purify them, it's useless. So the classical purification is by using centrifugation with a non-solvent. Usually you prepare your nanocrystals in non-polar solvents like toluene, hexane, and so on. You add to this mixture a polar non-solvent like methanol, ethanol, and so on. Your nanocrystals don't like it, they precipitate. you centrifuge it, you separate your precipitate from the liquid, and in the liquid you have everything which is in excess, your unreacted precursors, your extra ligands, and so on. You get rid of it, then you can repeat this process several times, and you get your nicely pure nanocrystals. This is probably by far the most popular purification way, but it has also its disadvantages. It depends on the solubility of your free ligands or other impurities in your solvent. For example, stearates are not very soluble. It's harder to get rid of them. And also, every time you add non-solvent, you precipitate, you purify, you lose some of the ligands from the surface of your nanocrystals. So they become less soluble. One problem. Another problem, you create surface traps. You lose your quantum yields. So there are some alternative purification strategies, such as chromatography or electrophoresis. Like this, you don't perturb that much the ligand shell, but it's harder to find the stationary phase to pass through the nanocrystals in a non-polar solvent. So, as usual, you have some advantages and disadvantages. Last word about nanocrystals ligands. Turns out that in addition to making them soluble in different solvents, in polar and non-polar, you can play with the electronic properties just by changing the solvents. For example, Edward Sargent from Canada, he has shown that in this case I think it's lead sulfide nanocrystals. If he uses some nanocrystals, he can dope some certain type of ligands. He can dope his nanocrystals negatively, so majority charge carriers are electrons, or just he's using different ligands, but always the same core nanocrystals. He can get them p-type. So this is very interesting for the electronic applications, for the diodes, for solar cells, and so on. You don't play with the chemistry of your core, just you replace your ligands. And you can, by playing with ligands, you can also shift the energy. As you remember, you can change the energy by changing their size, of course by changing the chemistry of the core, but also you have another tool, is you can play with the ligands. And as you change the ligands, you can shift your HOMO-LUMO levels just by ligand exchange. Last topic is metal halide perovskite nanocrystals. This is, I decided to make it separate because it's really a very particular topic. These materials, metal halide perovskites, they have appeared maybe like 10 years ago. They've been known for tens of years before, but metal halide ones for optoelectronic applications, they appeared like 2012 maybe. And right away, the efficiency in solar cells started to grow, and these days it has achieved already 25%. It means that it is higher already than the silicon solar cells. So it has created a phenomenon, a sensation in the world. Why is it happening? So first of all, they have very high absorption coefficients. In the form of nanocrystals, because you can get them as monocrystals, the single crystals, as the films, as the nanocrystals. In this course, I will talk, of course, about nanocrystals. And the nanocrystals photoluminescence quantum yield is 100%. So it is really impressive. And the emission is very narrow. For emission applications, it's paradise. They have very high defect tolerance. It means that if you introduce some defect into silicon, you kill the conductivity of silicon. In this case of the perovskite, it doesn't have that much effect on the electronic properties. You can easily tune the wavelength, and they are highly ionic with respect to classical nanocrystals. So the perovskites, they have this perovskite crystalline structure. It's an octahedron of halogens bound to a coordination center. In this case, most popular is lead halide. And in the cavities between those octahedra, to maintain the stability of the system, it's some large organic or inorganic cation like cesium or methylammonium. Usually you get them cubic. You can control their size. They are very monodisperse. They self-organize very nicely. Of course, they have ligands on the surface as any other nanocrystals. And the difference with respect to classical nanocrystals is that usually you tune the wavelength by tuning the size, and in this case it's less efficient, but what is extremely efficient is when you change the halogen. So AbX3, X is halogen. If you switch from iodine to chloride, you can get all the spectrum from deep red to deep blue, and you can get all types of alloys in between. So this is very nice, and the cherry on the cake is that it's very fast. As you can see here, you inject the halogen precursor and it changes the emission right away. In 2 seconds you have already a complete conversion of your system. So how we can synthesize it? We can first of all, is hot injection. It's the same old method. You use some lead salts in non-coordinating solvents, which you heat, and you inject cesium oleate under nitrogen flow, and you get this reaction. Is, as I mentioned, it's ionic, so it's very fast. It's easy to fabricate it, and you get it in several seconds. So I have a small video for you to show. So this is the precursors, and using the syringe, the guy has just injected the cesium oleate, and right away, instantly, you see that it is very luminescent, and they let it react for several seconds, and then we quench it with ice, because otherwise they will grow too much and they will coalesce. So just to show you that this synthesis is really simple and very fast. Alternative synthesis is what we call ligand-assisted reprecipitation. In this case, we mix all the precursors in some polar solvent like DMF, and we add it dropwise to some bad solvent, let's say toluene. And as you drop, you create this also supersaturation, which is assisted by the ligands which you use, by oleates, for example, and you get already in the solution, you get directly nanocrystals. So in this video, you can see, yeah, the pipette. You get some droplets, and you get directly formation in the solution, these luminescent nanoparticles, and as we drop more, they get more luminescent. We have more and more generation. Like this, we can get also very nice size dispersion of these nanocrystals. Last point is how we can control the morphology and the size of these nanocrystals. As two precursors, two ligands, we use carboxylic acids and amines. We can play with the temperature. So if we use high temperature and we play with the length of acid, we can get either smaller cubes or larger cubes. If we play with the length of amine, we can get nanocubes or nanoplatelets, which is a 2D material with one dimension much larger than the other. At low temperature, you can play with the thickness of these nanoplatelets. You can get 2 atomic layers, 4, 6, and so on, just by playing with amine chain length. So this is very similar of what I have demonstrated you for nanocrystals, for classical semiconductor quantum dots. So this is the end of this course. I have shown you some ways, some principles of the synthesis of semiconductor nanocrystals. As I mentioned, you can control their size by the time of the synthesis, by the solvent, coordinating or non-coordinate, by temperature, by ligands, by reactivity of the precursors, as it was the case for indium phosphide. We can control their shape by playing with ligands, by the ratio, by the temperature. We can control their optical properties, improve by the shell growth. We can get like this all different types of nanocrystals, ionic ones like lead halide perovskites, covalent ones like indium phosphide, and everything in between. I have shown you some non-toxic nanocrystals and water-soluble nanocrystals. So I think it will be useful for you. So thank you for your attention. Stop it.